Hello friends, in this lecture we will look at another method of quantization called delta modulation. If we have a continuous time, continuous amplitude signal m of t and it is sampled at discrete instants of time in pulse code modulation or PCM, the actual sample value, say m of nts, is quantized into quantization level. Each quantization level is represented by n bits. So if there are n bits, there will be 2 to the power n quantization levels. The dynamic range is divided in this L quantization levels. If we want to increase the resolution or accuracy of representation, then we need more number of levels in the dynamic range of the signal. The dynamic range is the difference between the maximum amplitude and the minimum amplitude of the signal. And the more the number of levels we need, the more the number of bits we need to encode each sample. Now it is noted that for practical signals, successive sample values do not differ much. And if instead of quantizing the actual sample value, if we quantize the difference between two successive sample values, then we can achieve quantization using fewer number of bits. The extreme case of it would be to have a 1-bit quantizer. A delta modulator is that extreme. It is nothing but a 1-bit quantizer in which instead of quantizing the actual sample value, we quantize the difference between successive sample values. Clearly, the dynamic range, that is the maximum difference between two successive sample values, is much smaller than the dynamic range of the entire signal, and therefore we can represent that using fewer number of bits. Of course, to maintain the accuracy of representation in a given limit, we need to sample the signal at a much higher rate than the Nyquist rate so that the successive samples are close enough to have a very good correlation. Once that is ensured, the difference indeed is quantized using just 1 bit, as we will see shortly, as if the difference between the quantized value and the actual value is positive, we encode it using, say, bit 1, and if the difference is negative, we encode it using as a bit 0. So it is worth noting here that whereas in PCM, the dynamic range is fixed, and to increase the accuracy, we need to use more number of quantization levels and therefore more number of bits per sample. In delta modulation, the number of bits is fixed to 1, and to increase the accuracy of representation, we need higher sampling rate so that the dynamic range of the successive sample values is reduced. So the idea here is that the dynamic range of the difference between successive sample values is much smaller than the dynamic range of the actual sample values. And therefore, instead of quantizing the actual sample values, quantize the difference between successive sample values, and that is the key principle of delta modulation. Let us understand this process pictorially. Consider a continuous time, continuous amplitude message signal m of t, and consider a time instant n ts for reference. The sampling instant prior to it is n minus 1 ts, and the succeeding sampling instant is n plus 1 ts. Now here, let's say this is the value of m of t. The actual sampling value of m of t here is mn, actually m of nts, which we represent as m of n with n in square brackets. And let us assume that the approximation or the prediction of the quantized value for sampling instant nts is this level m q subscript q of n minus 1. So mqn minus 1 is the approximation of the quantized value at the sampling instant n. Now, the difference between the actual sample value and the predicted sample value here is positive, and therefore our next prediction, the prediction for the next sampling instant n plus 1 ts, will be the previous prediction plus some constant delta, which is called the step size, and that makes mqn, which acts as the prediction for the next sampling instant. Now at the next sampling instant, observe that this is the actual sample value mn plus 1. The predicted sample value is mqn. The difference mn plus 1 minus mqn is negative. So the prediction for the next sampling instant, which will be mqn plus 1, is mqn minus some fixed delta. So this way this process continues, and what we get is a staircase approximation to the analog signal. This staircase approximation, this signal, staircase signal, is our delta modulated wave, DM wave. Because this staircase function can be generated from a given reference point just by knowing whether to go delta up or delta down, that message can be encoded in a binary digit stream, bit stream, as 0 and 1. For minus delta, it is encoded as 0. For plus delta, it is encoded as 1, and so on. So this DM wave can be encoded as a bit stream as shown here. And because we are just using 1 bit for representation, we are getting a significant compression here. This bit stream can be used for storage to store the data, or can be used for transmission. Let us try to understand this process mathematically. This is the block diagram of a DM transmitter. We have a message signal MT which has been sampled, and we have the actual sample values m of n here. So m of n represents actual sample value at t equal to nts. And let mqn minus 1 represent an approximation to m of n at t equal to nts. Now, the first step in DM wave generation is to compute this error signal E of n. So step 1 is to generate the error signal E of n, the difference between the actual sample value and the approximated value. And then in step 2, as we understood pictorially in the previous slide, that this error is quantized as EQN, and EQN is delta signum function, signum of E of n. Recall that a signum function, say signum of x, is equal to +1 for x greater than 0, and it is -1 for x less than 0. So here, whenever the error is positive, EQN will be plus delta, and whenever the error is negative, EQN is minus delta. And in step 3, this quantized error is added to the prediction at this instant for getting the approximation for the next sampling instant. So we get MQN, the approximation for next sampling instant as approximation for the present sampling instant plus the quantized error. And then the cycle goes on. So essentially what we are doing is that we are getting the quantization error EQN as either plus delta or minus delta. Plus delta may be encoded as 1, minus delta may be encoded as 0, and this results in a bit stream of ones and zeros which can be stored or transmitted. So as we can see here, this is exactly what is shown in this block diagram. The first equation, En equal to Mn, this signal minus MQN minus 1. Now this En is quantized using 1-bit quantizer. We get this EQN, the second step, and then this EQN is added to MQN minus 1 to generate MQN, the third step. From MQN, we get MQN minus 1 using a single bit delay element. And indeed, this process, the third step, is what is also called accumulation, and this what is achieving it is an accumulator. And here this EQN, which is either plus delta or minus delta, is encoded as ones and zeros, say 1, 0, 0, 1, and so on. So we get this bit stream 1, 0, 0, 1, 0, and so on, and that is transmitted. So this is the DM transmitter. Similarly, at the receiving end, this 1, 0, 0, 1, 0, whatever was transmitted is received, is decoded, so that we get EQN back here. And to EQN, if we add MQN minus 1, we get MQN here, and MQN is nothing but the staircase function as we see here. And if that staircase function is passed through a low pass filter, we get a smoothened version of the signal, and that is a reconstructed signal. We can represent that as M hat T, an estimation of the actual original signal M of T. So mathematically, for reconstruction, we have MQN minus 1 plus EQN equal to MQN. The MQN is of this form, some staircase approximation of the original message, something like this, depending on the message, of course. And when it is passed through a low pass filter, we get a smooth version of it, and this is our M hat. So the key benefit of a delta modulator is its simple circuitry, because it just requires 1 bit for quantization. So its circuitry is simple, and therefore its implementation is simple. Further, because of 1 bit representation, it results in very low bit rate, and it is therefore also used for compression. It may be noted here that though we get compression in the sense that we are just using 1 bit for representation, but for effective implementation of a delta modulator, we need high sampling rate, much higher than the Nyquist rate, and therefore this benefit is limited to some extent. And as they say, there is no free lunch. There are some drawbacks associated with delta modulator as well. So it has higher quantization noise compared to PCM. Indeed, there are two types of noise which we will discuss in the next lecture. The first one is slope overload noise, and the second one is granular noise. This granular noise, as we will see, is similar to what we have in PCM, but the amount of this noise, the quantization noise power in case of DM, delta modulation, is much higher compared to PCM. We will also show that in the next lecture. So that's all. Thank you very much.